So let's think about what the velocity is. I was able to find in those last two slides, I was able to find the horizontal speed and the vertical speed, but if I want to consider the velocity, remember velocity is a vector. This has a size and a direction. So it's going a certain speed. Eliana is riding on this motorcycle a certain speed in this direction where I'm moving vertically and horizontally. And I want to capture both of those things at once. I can't really do that with the equations that I created before. So I can express this vector of the velocity using both x and y at the same time. So what I was able to accomplish in two equations, I can actually combine into one expression and compare that horizontal and vertical velocity at the same time. And that's what we're going to do. So let's just jot down what we know so far. The horizontal velocity we got from our other equation, and that was 3 inches per second. And our vertical velocity is -1 inch per second. And basically what I want to do here is I want to combine the horizontal and the vertical velocity into one vector. And we call this a velocity vector. If I'm moving to the right 3 and down 1 every second, this component form vector, this describes my velocity. So every second, this vector is moving across this path of motion. Notice this is different than the speed. This is just my velocity. I go over 3 and down 1. So this isn't really to scale here, but let's say that this is over 3 and down 1. This would be 1 second, and then over 3 and down 1 second. Each one of these is the size of my velocity vector, and the size of my velocity vector is how much distance I've traveled in 1 second. And this is irrespective of the time. So what this length that I've achieved or that I've drawn here is essentially what the speed is. So what am I getting after here is the speed of the motorcycle moving across this rug is equal to the magnitude of my velocity vector. This gives me a horizontal and vertical component of movement, and if I want to find the actual speed, I need to find the size of that velocity vector. So in this case, the speed is going to equal the square root of 3 squared plus -1 squared, which is equal to the square root of 10, which is approximately 3.16 inches per second. So this is just how fast she's moving across the rug. This describes the actual position, or rather direction, of this vector. So a vector equation. Can I use that vector that I just found to describe in one equation where this motorcycle will be moving across the rug? Before I kind of had two equations, one to describe just the horizontal movement and one to describe the vertical. Can I combine these two things? Yes, I can. So just like thinking about what a linear equation looks like, where I had y equals a plus bt, where I had like a start and a rate of change, I'm going to use that same type of idea to kind of build a bridge to my vector equation. And in this case, I'm not using just a y or just an x, but I'm using x and y. The xy position is going to be given by my starting point. In this case, I'm starting at 0, 24. And I'm going to add, in this case, I'm not going to write bt, but I'm going to write tb, and I'll explain why in just a second. And then this is going to be my rate of change, this thing right here. And the rate of change is my velocity vector, 3, -1. This right here is my vector equation that describes where the position will be of the motorcycle on the rug for any given time t. And the reason why we put t here is because t is a scalar, and by convention we put the scalar in front of the vector that we're multiplying this thing. So this right here is a vector equation. Right here I have my starting position, and right here I have my velocity vector. So again, think of this as like slope-intercept form of a line. I have a start and I have a rate. That's the same thing that's going on here, but now it's in 2 dimensions. So let's talk about parametric equations and vector equations. Now, believe it or not, we actually already saw parametric equations. By definition, parametric equations, it describes the x and y movements individually, and t is the parameter. So this is actually what we already did before, where we had 2 equations. We had x equals 3t. This describes my horizontal movement, and y equals 24 minus t. This was my vertical movement. And in general, we have parametric equations in the form x equals a1 plus b1t, and then y is going to equal a2 plus b2t. That's my parametric equation. Vector equations, we just saw an example of that. That describes position vector given a time t. So we need to have a position vector and a velocity vector in order to write this thing. So the general form we use in just regular vector form, we call the position r is going to equal the position vector a plus t, the scalar t, times vector b. That's our general position or general equation. We also see this in component form as xy equals some a1 b1, a1 a2 plus t times the velocity vector b1 b2. And hopefully you're seeing that's kind of the connection between vector equations and the velocity, or the vector equation and the parametric equation. So this right here is my general form of the velocity vector. In our example, we saw the vector equation that we just got from that last slide there. So we can use either one of these. We can use the set of parametric equations or this vector equation to describe the same movement over time in 2 dimensions. Now really there's a third type of equation, Cartesian equations, and what that is just showing the path of x and y, and the advantage of this is you can get a full view of what the actual path is. The disadvantage of this is there's no time involved in this. This will only give you position. Irrespective of time. And so how do you do this? Well, if I wanted to find what the Cartesian equation is of this path using just x and y, then what I'll need to do is I'll have to start with my parametric equations. And in this example here, I've got x equals 3t, I've got y equals 24 minus t, and what I need to do to get this down to just y's and x's is I need to solve for t and substitute. So it's basically a basically a substitution problem. So let's solve this equation for t. X equals 3t, or t is going to equal 3 over x. Oh, backwards. T equals x over 3. And then I'll take this x over 3 and I'll substitute that right in for this t. So then I get y equals 24 minus x over 3, or I can write this in a more familiar form, y equals negative 1/3 x plus 24. And if you were to graph this line, you would get the exact same graph as we saw on that rug, but now we just have no clue at what time we're at with any given position. So there's advantages and disadvantages. So 3 equations of forms that kind of talk about similar things. They each have pros and cons, but now we have this whole new way to include time within an x and y position. So as an example, let's do these 2 things. Let's write out a vector equation and parametric equations of lines that pass through this point and in this direction. So let's start off with the vector equation. I need to consider this as my position, and I need to consider this direction vector is my velocity. So if I'm going to write this as r equals a plus tb, my vector equation, this is going to be the vector xy is going to equal, here's my position vector, 3, negative 4, plus t times my velocity vector 1, 4. And really that's it. That's the first one. The second one is to write the parametric equations. And the beauty about this is we've really already done the work for us. The parametric equations, really, if I just isolate each component of my vector equation, I have the parametric equations. So x is going to equal 3 plus t, or 1t, and y is going to equal negative 4 plus 4t. That's it. All that there is to it. In this next example, I want you to try on your piece of paper what the next problem looks like, and I will show you the answers when you're ready to hit play. All right, here are the answers for this problem right here. Hopefully it went all right. And so really what we've done is we've kind of introduced a new type of equation using vectors that we already know and love, and now we can kind of incorporate speed and distance and time and position all over the place to have these great lines with 3 variables, really, an x, a y, and a t.